Hi, good morning. My name is Dibyendu Das and I work for Intel compiler team. And first of all, let me thank the organizers for giving me a chance to speak at this particular conference as part of this tutorial. And you would have already heard my colleagues Sandhya and Ramakrishna talk about various aspects of this big data and DL4 code, setting up, the initial, groundwork. Ramakrishna has also talked about how we encode various kinds of compiler representations, especially its intermediate representations like the IR. And so I'll take it from there and show how some of these representations are used internally inside the compiler. And sometimes new representations may be required. Sometimes we can use some of these existing representations. So, okay, let's move on. Um, the brief agenda. Today I'll give you a very brief background of compiler optimization passes and what we're going to talk about. Then specifically 4 different problems will be placed in front of you, and we'll see how these problems have been solved using deep learning, and we'll look at various aspects of the compiler as part of that. And these are deep tune, ethymal, graph coloring based register allocation, and auto vectorization. And then finally, I'll give you, a very 20,000 foot view of how the things are looking today and what can it be going forward. Okay, so to give a brief background, if you are familiar with compiler optimizations, you would know that a compiler optimization is usually created in terms of passes. And when we say passes, it means that you have the program initially lowered from the front end in some form of an intermediate representation, as you can see, which is called IR. And Ramakrishna has already talked about IR to VEC and things like that. And on this IR, we initially do some analysis to see, okay, can we do this particular optimization? And then we actually do the transformation. For example, we want to do loop unrolling, we want to do vectorization, we want to do inlining, and so on and so forth. And in a traditional compiler, or even in any of the compilers that you'll see in research, the program optimizations are usually set up as a sequence of passes, like you will have pass 1, you'll have pass 2, all the way up to pass n. And in each pass, in general, you will have an analysis phase and a transformation phase. And finally, once all the passes are done, you have fully optimized your program as best as you can. You will then do a code generation and you generate the optimized program in your target language. So then when we say compiler optimization passes, it really will mean a group of analysis and transformation, but sometimes it may just mean, I may say just the analysis pass, or I may try to say just about the transformation pass. Now, what happens today in most of the modern compilers is that lots of these compiler optimizations depend on very carefully constructed heuristics. And when we say carefully constructed heuristics, we mean that the programmer or the compiler designer knows which optimization order to apply. That should I do pass 1 before pass 2? Should I do pass 15 before pass something else? Because those orders have a certain reason to be put out there in terms of how the optimizations play out. And also in many cases, there are optimizations you want to do early, some optimization you want to do late, and sometimes also there's a dependence, like you cannot do a pass before something else has already happened. For example, many of the loop optimizations may not happen unless you put the loop in some form of a normalized or canonical form, things like that. Also things like, if you are going to write an optimization pass to inline functions, you would want to know which functions should be inlined, right? And are there functions which are hot? Are there functions which are cold, etc., etc.? For example, in scheduling and register allocation, you have similar problems where heuristics are required because we really don't have polynomial time solutions for these problems. In loop unrolling, we'd like to know how much to unroll the loops by, what is the unrolling factor. Once again, these are kind of based on heuristics because you'd like to figure out by unrolling what kind of gains we'll get from the compiler because each machine may behave differently when you unroll the loops. So these heuristics are developed and maintained by compiler engineers, and as a result of that, they are not always scalable, because these are really very, very complicated pieces of software, and also these heuristics are difficult to adopt to different hardware because even though we'd like to make them as general as possible in many cases, we'll still need to take care of many hardware characteristics. And these come out at different knobs. For example, for loop unrolling, the same unroll loop may behave differently for different architecture, like an x86 versus ARM versus something else. Also, some of these heuristics are fragile because, as compiler developers, we work for companies and there are, some customers having some issues with performance and we quickly put a fix and that may not work in other cases, cause regressions in certain performance benchmarks and so on and so forth. And the space of possible optimization is really, really vast, making it very hard for the writers to design heuristics, right? It is not always easy, even to actually organize the passes in an efficient manner. As a result, what has happened is many compiler optimizations, which have been written, let's say, 5 years back, 7 years back, 10 years back, are already out of date, are purely poorly tuned. New compilers who come in and try to maintain that code really don't have an idea as to what's going on. So many issues. Okay. So ideally, what do the compiler writers want? So ideally, what they would want is a compiler heuristic or optimization design such that it'll execute the code faster. It'll have smaller code footprint. We want to have reduced power, and all this while being scalable and better understandability of the code written and things like that. So machine learning has been used in the past. It's not really totally new. So what folks have done in the past, and you can see from this diagram in this picture, which is taken from Wang and Michael Bowen's paper, is if you have a program in which some intermediate format, uh, some kind of feature engineering was done. For example, if you have a block of code, like how many instructions are there in that block of code, how many load instructions, maybe how many store, is it branchy, it is not branchy, do you have the numbers like the cache miss rate, etc., etc. And these are the kind of features you would extract from a block of code, and then you'll train various a bunch of programs using these extracted features, and you will create a supervised machine model based on that. And once you deploy for a new program, once again, you have the extracted features, you apply the model, and you get your desired results, predictions. So this was uh, a flow which have been applied. Though I have worked in many commercial compilers, and I still don't know of a single commercial compiler which have really applied even older machine learning techniques to a large degree. It has largely been absent from the commercial compilers. Yes, some of the research compilers have adopted them, but not commercial ones. But recently, with the introduction of deep learning, various techniques in deep learning, reinforcement learning, people have renewed interest in that, where you really don't want to do feature engineering. You just take the code as is and you learn your features automatically through the model, and then apply and do your prediction. So that's what I'm going to talk about by looking at some examples. So the first one I'm going to talk about is called Deep Tune, and this is one of the first work, I should say, which looked at end-to-end deep learning of optimization heuristic. I think this work was published around 2017 by Chris Cummins and others, and Lstm. So you've already heard of Deep Tune from Ramakrishna's talk to some extent, but I'll go into a bit of depth as to how the whole thing is working. So the idea of deep tune is to ask this question like, can we do an end-to-end? When I say end-to-end, like you take a program and then finally at the end you do a prediction based on that program. Can you do this kind of an end-to-end prediction using good machine learning deep learning techniques? And the particular problem this paper handles, it handles actually several problems. I'll just focus on one particular one. Is called optimal mapping of heterogeneous parallelism. And what it means is people who are familiar with GPUs would know that there's a well-known open source language called OpenCL, which is kind of similar to CUDA if you are familiar with NVIDIA's GPUs. And so you write what are known as kernels. These kernels written in OpenCL go and execute on the GPU. But it's not always true that the performance is great, because sometimes the code that is written in the kernel or the algorithm that you are expressing in that kernel may have maybe a lot of branchy code and a lot of other characteristics which may not make it a good candidate to run on a GPU. As a result of it, a kernel may actually run better on a CPU. So this particular problem in Deep Tune wants to predict whether, given a particular kernel, is it good to run it on a CPU or is it good to run it on a GPU? And this is being done in an end-to-end fashion. And why we call it end-to-end fashion? Because it takes in OpenCL code and it does some passes like it. I'll explain about what the source rewriter is, kind of normalizes the code in some form, then does some encoding of its various tokens, creates an embedding, and then has some layers of Lstm in addition to some auxiliary inputs, which are like characteristics of the machine it will run on the CPU or the GPU and things like that. And kind of concats all this, vectors and passes through a batch norm and a dense mapping to finally predict whether the device needs to be mapped. The OpenCL kernel needs to be mapped to a CPU device or a GPU device. Okay. And if you look at the deep tune components more closely, right? So you have initially the language model. So the kernels really look like this. You have the keyword kernel in front of it, which specifies that it's a kernel. And then you have the name, you have these parameters, there are various keywords like global and local and things like that, which you need not be bothered about right now. And then inside the kernel, you'll see really, code similar to C or C++. And you have some concepts of get global ID, which is like a thread ID and on which of the GPU cores it will run and things like that. So this is the language model. And so the first thing DeepTune tries to do is creates what is called a source rewriter. So it kind of normalizes this code by kind of normalizing all the names. For example, you start the memset kernel name with A, the capital A, and then all the parameters are given names like A, B, and C. And then inside, once you get inside the body of your function, you start using other small letters and things like that. So that kind of generalizes the functions. You do different dependencies on special names of the identifiers and things like that. So once you do a source rewriting, then you kind of tokenize it and encode it. This encoding, as you can see, is based on tokens. So for example, each individual token like kernel is given a particular number, space is given a number, void is given a number, and then because we are going to use the letters like A, small b, small c, etc. All of these are given numbers. So these are all the the encoding that will happen. So if you can see below, for the kernel above, you'll have this kind of now, if you look at it, once the encoding is done, right, this encoding actually is not great in terms of the fact that it's really a very sparse encoding. And then we really want to make it into dense representation. So what we'll do is we'll add an embedding layer to that. So once your encoding is done, as you can see here on the left hand side, you go through your embedding And currently in DeepTune, the embedding has a length of 64 in the output. And after you have finished doing that embedding, you have a two-layer LSTM. These two-layer LSTM both have hidden units of size 64. And then we have a sigmoid activation function for the last layer of the LSTM. And then we also have some auxiliary inputs. Now, the auxiliary inputs in this particular case are nothing else but some specific GPU values called workgroup size and data size, which are specific to GPUs. And these are also taken as inputs. And what happens after that is we concatenate the output from the LSTM, right, and the auxiliary inputs, and then pass it through a batch norm and a couple of dense layers. And then finally, what you get is through a categorical cross entropy, we get the values of 0 or 1 to specify whether we should map it to the CPU or to the GPU. Okay, and this is the full, the end-to-end model starting from OpenCL source code, right, all the way down to the prediction. Now, as you can see here, the encoding and the embedding is not similar to what Professor Ramakrishna and his team did with IR2VEC and things like that. But please remember that this work actually preceded their work. And so here you can see the training happens end to end and along with your various training sets. So it's not that we have any pre-trained vector embedding for your keywords or tokens or things like that. So if you want to visualize DeepTune, right, and its various layers, you can see here that we have the code, and then it has been rewritten in a certain format so that all the codes have a similar kind of input, so that we can extract the structure and not bother about the various parameter names, the function names, variable names, and so on. And then you go through encoding, which is then followed by the embedding. And once you are have embedded all your tokens, you can see how they line up in your vector space. And then once you go through your batch norm and then CNN, you can target, you can see the various hardwares that were targeted by this particular DeepTune, including the various AMD GPUs and the NVIDIA GPUs. So coming to performance, if you look at the performance that Chris and others got for DeepTune, it was pretty good. If you look at optimal static mapping of the same kind of kernels, that is like, you just look at a few characteristics and map them, then you have only about a 50-60% accuracy, while you do like a handcrafted feature engineering and other ML techniques, you achieve something like 70% plus, but DeepTune actually improves on it by more than 10%, and we achieve an accuracy of close to 84%. And this is over a series of benchmarks like NAS parallel benchmarks, Parboil, Polybench, Rodinia, Shock, and some of the SDKs released by both AMD and NVIDIA. So I also have a slide which actually compares DeepTune's token-based IR encoding versus IR2VEC, and you'll be pleased to know that IR2VEC actually improves upon the kind of encoding DeepTune uses by quite a bit, right? Because if you look at the IR2VEC, once again, you've already been told that IR2VEC have different kinds of flavors, like the symbolic and flow aware and things like that. We are actually, close to 15-20% better than DeepTune, right? Especially on the AMD machines. On the NVIDIA machines, the numbers maybe are slightly lower, but we still can see a gain of close to 7-8% from using IRT. So that completes the first optimization I wanted to talk about, which is a kind of end-to-end optimization, but one of the first optimizations that was worked on. And as you could see there, the tokenization embedding techniques were all pretty primitive, right? And the question that was asked was, given a particular kernel, could I map it well to a CPU or could I map it well to the GPU? Now let us go to a slightly different problem. This work was done at MIT under Professor Saman Amarsinge and by student Charit Mendes. So this is slightly closer to the hardware. And in the first, we took an end-to-end problem. Here, what Professor Amarsinge and the student tried to do is to predict the throughput of a basic block by using DL techniques, and they called it ITMOL. So let's introduce you to the problem. So there's this concept of basic blocks in compilers, and is nothing else but a contiguous series of, it's either intermediate code or machine code or actual assembly. And the characteristic of a basic block is you can only jump from the top, and you can, jump in from the top and jump out at the bottom, right? You cannot have a jump from inside of a basic block. So you can think of it as a piece of code which is straight line. And in many cases, as part of your performance estimation and various other performance work that you do while either developing new architectures or evaluating compiler code or evaluating performance of various tools, you may need to figure out as to how many cycles will a bunch of assembly instructions take. And Professor Amarsinge and others, they tried to solve this problem using deep learning. And what happens in these cases is you usually have these analytical models. Like, for example, for the famous LLVM compiler, there's something called LLVM MCA. In Intel, we have what is called IACA. And these are models which are usually used to measure or predict what kind of throughputs or what kind of number of cycles that will be consumed by a particular set of instructions. Now, accurate modeling of processor core is an extremely complex task, and people who have tried to do that would know that it's quite error prone. It's very easy to omit details when you're doing that modeling. Sometimes specs are not accurate. Some details sometimes are proprietary if you're trying to build an open source tool and you may not get all the information. So you can see the problem here at the top. This is the core of Cascade Lake. I mean, it's still a very high level, right, view where you have the front end, which takes in your instructions. It does decoding. You have an instruction queue. You have your mu-up cache. You have your branch prediction units. You have your load store buffers. You have, your integer unit. You have your vector unit. And frankly, you have to model all of these and figure out, like, if I have a bunch of instructions like this on the left-hand side, then how many cycles will actually be consumed? And please note that these are all out-of-order machines, right? These are not in-order machines. That they are not really executing an instruction one after another as it appears in the sequential order in the core. They can execute in any order as long as the dependencies are met. So it's a hard problem, and in this work, uh, machine learning was used, and it's just not traditional, but basically a deep learning model was used. So what was done is 1.4 million basic blocks were extracted from various benchmarks, right, of instructions from Spec 2006, Spec 2017, NAS parallel benchmarks, very well-known benchmarks. And then a neural network model was devised. I'll talk about the model in the next few slides. A neural network model was devised, and then the ground truth was taken by actually running. It's not a model running, but actually running that sequence of instructions on an actual hardware, right? Let's say Cascade Lake or Skylake or any other piece of actual hardware. And then, the training happens by looking at the difference between your predicted output from the model and the actual output, and you feed back the usual sequence that you have in machine learning. So what model was actually used for this purpose? So this is actually very interesting because Ithamal used, once again, an Lstm, but a two-layer Lstm, right? So you saw in the deep tune work that for the end-to-end deep learning, a two-layer Lstm was used. But here, instead of using a two-layer Lstm, there was this hierarchical STM. Now it's also two layers, but it handles the encoding at a different level of granularity. So the first level of granularity is at the instruction level. So for example, if you have this particular instruction, right, move ECX 0x02. So it is first, once again, it is canonicalized, right? What we saw earlier, which was like the source rewriter. You have the move, you have your space, constants, etc., and token. Similarly, let's say you have move followed by add, you have your add canonicalized, right? So once you have a canonicalization, you do a lookup table. So here it is token embedding lookup table. The embedding is done as once again as part of the end-to-end model generation. And so you have now your vector encoding for your move token, for your space token, for your constants. Now, by the way, the constant values are all modified to just have the value CONST. It's not like 0x02 as a different embedding from 0x01 and things like that. All of them get a single const embedding. And then that is like the vconst, right? And then all the other your vector embeddings for all your other tokens. Similarly for this. Now, if you see what happened in the first layer, which is called the instruction layer, is this entire series is looked as a sequence of LSTMs, right? As sorry, as an LSTM, but what we have is each instruction is fed, right? Each instruction is fed to the LSTM, right? So, for example, when you get the first instruction, v move vs, it will fed to LSTM, and you get a particular output from that LSTM. Okay, and then once again, once you have v add vx, this particular token, you feed it to another LSTM, and you the other output from that. So this is the first layer of your LSTM. And then the layer 2 is at the level of your basic block, in the sense that these are for the individual tokens, while these will now take all the instructions as your vectors. For example, you have one encoding now, as if one encoding or one prediction for your entire vmove instruction, one encoding or prediction for your HAD, and then this is fed to another layer, right? This is fed to another layer. Now, as you can see, the number of instructions can be large, right? It can be, usually a basic block can have 200, 300, 400 instructions, 7 instructions. So the LSTM will have so many units. And so finally, out of these two-layer LSTM, we get a prediction for you get the encoding for the block, and then finally you get your throughput through several layers of dense NLP, and you get the final value of your prediction. Now, Ithamal actually does very well when you compare it to the model-driven tools like ISCA or LLVM MCA. And as you can see, over various generation of Intel hardware like Ivy Bridge, Haswell, Skylake, Ithamal has shown almost like much lesser error rate and much better accuracy for all of these hardwares, you can see the accuracy is close to 90% plus. I mean, in most of the cases, 91%, 92%, while the other tools suffer from about, accuracy close to maybe about 75 to 80%, that kind of levels, right? So, using a two-layer, let's say, two hierarchical layers of LSTM, Ithamal is able to get much better performance. Now, you may now ask is, why can't we use a similar hierarchical level LSTM for, let's say, a deep tune? And it's like, yeah, it's possible. Like, it's not that it has not been tried. So where you can look at, each, let's say, a sentence, what you call a sentence or a statement in your OpenCL code as the first level, and then you can look at the sequence of statements in your full function as a second level of LSTM, and then maybe you may be able to get better accuracy than what DeepTune provided. Okay, so that's completes my presentation for the second optimization that I was going to talk about. And the third one, which is a work done some years back by myself and some of my colleagues at AMD, is called a DL-based graph coloring register allocation. And let me introduce the problem to you. So many of you may know about graph coloring. It's a very important problem in computer science, and what you actually require is to color a graph such that two adjacent nodes should not have the same color. So, for example, in this particular graph on the right-hand side, the graph has a chromatic number, which is called the colorability number, as 3 because you can color this graph with 3 colors such that no edge has 2 nodes on its 2 ends having the same color, right? And this has enormous problems in this is enormous impact on various aspects of computer science, and especially in compilers, because in compilers register allocation is usually viewed as a graph coloring problem, and we'll see why. And now you know that machines have restricted number of registers, and keeping variables in registers as much as possible will speed up your program because you don't need to go to memory as often. So the way the problem is looked at is, let's say you have this kind of code that I show you on the right hand side, and you have this variables G, H, F, E, M, and so on, and we want to know, okay, how best can you keep them in registers? And the way it is formulated is we define something called live ranges. Live ranges is nothing else but the point at which that particular variable got defined and the point till which it gets used last. So, for example, G here, if you see, start getting used here, but its live ranges ends here because there's no other use of G after that. So once you create these live ranges, you have something called an interference graph. And what does interference graph mean? Interference graph means that you need to know which two live ranges overlap. And why is it that important? It is important because if two live ranges overlap, then you cannot give the same register to this variable, right? Because then they will thrash each other and give incorrect results. So, for example, you can give the same register to K and H, okay, because their live ranges don't overlap. But you cannot give the same register to K and L or K and G. So as you can see, if you look at the node K, you will see with what other various live ranges does it overlap, and then you draw an edge along that. And as a result, you get what is known as the interference graph. And then if you can color the interference graph, the chromatic number of that will tell you the number of registers to be on. Okay. So that's a particular problem. And then how did we try to solve the problem? So we tried to solve the problem by viewing this as a sequence-to-sequence translation via Lstms once again. And we look at the adjacency matrix of this particular interference graph. So we take the adjacency matrix of the interference graph, and then we say that, okay, I can encode each adjacency vector of this adjacency matrix, and each of them will go to one of these, LSTM instances, right? So this is like a V0, V1, V2, all the way up to Vn minus 1. And we have 1024 hidden units per LSTM, and we create this 3-layered LSTM, and then there's a dense ReLU unit. And the output of this is a value of a color. Okay, so right now this has been posed as a regression problem, but we can also do it, as using binary cross entropy and things like that. So this will be the overall structure where we encode the entire interference graph into this particular adjacency. Now, just to see what happens. Now, even if you do this kind of modeling, there's no guarantee that you will have two nodes which are adjacent not having the same color. So that's one problem that we face. So as a result of that, we have devised our algorithm is not really a pure DL algorithm. It's a kind of a hybrid DL algorithm because we apply the DL algorithm and we know that some nodes may have invalid colors, and we apply what is called as a color correction phase. Okay, what is a color correction phase? Is nothing else but we check after the DL has applied all the colors that are we getting the right colors? If not, we do a color correction. Now let me explain using this particular example. One of the main reasons why we have to do this is, it is very difficult to encode constraints in LSTM that two adjacent nodes cannot have the same color. Now you may ask, okay, why not use a kind of a reinforcement learning technique? And yes, there is actually quite a well-known paper from engineers at Baidu where they do graph coloring using reinforcement learning, not register allocation, by the way, but just graph coloring in reinforcement learning. But if you look at the algorithm, it is complicated and it actually takes a lot of training resources in terms of hardware. And they really had to, I think, use a pod or a super pod from NVIDIA to run their reinforcement learning algorithm. So this is one of the issues, which you'll see that we have been talking a bit about LSTMs. I'll also talk about one particular example of reinforcement learning, but in general, reinforcement learning based algorithms may have a lot of requirements on the hardware. Anyway, just a digression. So to come back to the problem at hand, what can happen is because it is difficult to encode constraints in LSTM, once you do the training and you predict, you may actually have invalid colors. And let's see what happens. For example, this is a famous graph found in literature called the forest fire graph. And when we apply our 3-layer LSTM on this, the forest fire graph colors it in this manner. The DL algorithm colors it in this manner, and we get a chromatic number of 5, right? Now, so we are supposed to get a chromatic number of 5, but at this point of time, it uses only, you can see C1, C2, C3, right, and C4, 4 colors, right? So we are actually coloring with less than the chromatic number, which is not possible. So obviously, we'll have some invalidations. And so you can see here that both this edge, right, 2 to 3, both of these nodes have color 3. Similarly here, between 1 and 5, both 1 and 5 have the color 2. So out of all the edges, these are the only 2 invalid edges. And what we do is we apply a normal, regular algorithm called color correction. We look at all these invalid edges and we try to break the color by either giving it a new color or trying to reuse a color. For example, for C1 to C5, we can remove this invalid edge by giving it, color C3, because none of its neighbors have C3. So we do not need to increase the number of colors. But here, to break this invalid edge, we have to give a new color. So at the end of the day, we actually are able to color this forest fire graph using the same coloring number as its chromatic number, which is 5, but by using a mixture of a DL-based algorithm and a normal color correction phase. Now, this is kind of novel because there's not much of work that has happened in this kind of algorithms where we'll see a mixture of a DL and a normal algorithm trying to solve a problem in this kind of areas. Okay. So how do we use it in registry allocation? Now, this has not been implemented. This is more of kind of design. So if you are familiar with the famous LLVM compiler, you will know that LLVM has what is called as a greedy register allocator, and there are various passes. I'll not go into these passes because it's a bit complicated, but let's put it this way, that there are several passes to the LLVM's greedy register allocation algorithm. And so what we do is, this is a heuristic-based method, as we are discussing, like how do you define the heuristics? How do you, do all these various phases properly such that for millions of programs, for billions of programs, you are always generating pretty good register allocation. So what we do instead is like, okay, we have these LLVMs register allocator, but from the live interval analysis, we can collect our interference graph, and then we push it through our LSTM-based model, and we predict the color or the register assignment, and we see, right, compare it to LLVM's GRA, and the full code is in the, the results are in the paper. I'll not show it here, but if you look at the results, you will see that we do as well as the GRA in many cases, and actually exceed the performance of GRA by 5 to 10% in several benchmarks that we tried. So it shows that this technique definitely has a lot of promise, though this has not been really written inside the LLVM compiler yet. We collect the interference graph from the LLVM compiler, and then this is still sitting outside the LLVM ecosystem, and we do our stuff. Okay. Okay. So that completes the third optimization. So we are now seeing three optimizations: one end-to-end using DeepTune. We have seen one kind of a back-end optimization. We're trying to predict the throughput of a bunch of assembly instructions. We have now seen how possibly we can use deep learning for register allocation using graph coloring. And all three of them coincidentally are LSTM based, because if you think, if you think of programs with a sequence, right, sequence of tokens, sequence of keywords, variables, whatever, and then it probably has a natural affinity towards NLP sequences or other sequence-based models that we have seen. But what we are also seeing that, and we just talked about a bit in the earlier work, that if you try to model everything using LSTMs, it's probably not possible because you will have correctness issues, and unless you can fix those correctness issues. Now, for example, in register allocator, we could fix it using an algorithm, post-pass. So if you cannot fix it, it's a problem, right? You cannot really apply it because you'll get incorrect code. So a lot of reinforcement learning based techniques are also becoming popular, and I'll talk about one of them. This is called auto-vectorization using imitation learning, and this once again is a very new work published in NeurIPS, I think about a year back, and once again comes from Professor Amar Singh and Charit's team. So let's first tell you what the auto-vectorization problem is, and then we'll go in brief, because RL is much more complicated and involved. We'll have a slightly higher level view of things here. So auto-vectorization, which is a popular phase in, or a pass in optimizing compiler, consists of two things. One is you have loop auto-vectorization. That is, you have a loop and you're trying to vectorize your loops. Or you have what is called as SLP, or superword level problem, which is the problem that is being handled in this particular case. So what happens in SLP is there's no loop, but you have a sequence of instructions, and the idea is, instead of doing all this scalar, can I vectorize it and use vector instructions, right, to generate your code. Now, for example, you can see A1, A2, A3, A4, A5, and they're instead of doing A1, A2 separately, you can put them in a vector register and do it together, and generate vector code. And the idea is, can we do this? And this is a well-known hard problem, because you never know, how you want to pack. It's called a packing problem. I want to pack A1 with A2, or I want to pack A1 with A3. Do I want to pack A2 with A4? So a lot of possibilities. So I really want, currently they're all heuristic driven, but I really want a machine learning model to learn and do this for me. So as you can see here, like, though I can pack A1 and A2, if I try to pack A4 and A5, it's wrong. And why is it wrong? Because A4 has a plus operation while A5 has a star operation. So really, these are not what are called as isomorphic operations. So you cannot really pack A4 and A5 because they have to be isomorphic in terms of your operators to be packed. So you really cannot have very naive ML strategy, because you have to look at various things. You have to look at correctness, and that's where RL comes to our rescue. So in this particular case, as you are all very familiar, that this is modeled as a markup division process. And in this particular case, we have the state, which is like initially you have a totally non-vectorized code, and then we'll have partially vectorized, and slowly you go to the state where you vectorize as much as possible, right? And so each state will have, for example, as you can see here, each state has its code, which is, let's say, unvectorized here, and then you have to choose a valid action. And the valid actions can be, as I said, there are various kinds of packing. I can do pack A1, A2. I can pack A2, A3. I can pack A3, A4. Actually, I can even pack A1, A3, right? And so there are various valid actions possible. And when you say that there are various valid actions possible, now, why we have not put A1, A3 is the fact that sometimes packing non-contiguous memory operations, so for example, A1 and A2 are contiguous, but A1, A3 are not. Packing non-contiguous memory operations may have a cost in terms of your instructions. You cannot really load and store non-contiguous instructions, non-contiguous elements in memory so easily. So that's one of the reasons we have avoided A1, A3. But if that is probably allowed by a machine, you don't have a very high cost, you can do that too. So we have to choose a valid action. So here, let's say the valid action is A1, A2, and then we can actually go to vectorize A1, A2, and that's the new state. Okay, and then you have this new state, which is A1, A2, and now we say, okay, what is the valid action? Okay, my valid action only right now is just A3, A4, and I do this, and you get a new state. So right now, maybe you cannot do anything more. So for each state, you also need to know your rewards. So maybe rewards is in terms of like how many instructions actually need to be generated to do this vectorization in your hardware, something like that. This packing problem can be actually be done either bottom up or top down. I'll not go into details, but there are advantages in both sides of things. But in this paper, they figure out, I think, if you do top down, you probably gain a bit in terms of performance. And it's a bit of a busy slide, but I'll just go very quickly. So if you look at MD formulation, the state details is just not as simple as what I showed you earlier. So here, what's going to happen is in the state, you actually have the nodes, which, for example, in the left-hand side, this is your code, A1 equal to C1 by L1, where A2 equal to C2 by L2, where L1, L2, L2, these are all memory accesses, and these are like, some variables which you have. And so your state actually encodes various things. Like, for example, this dotted edge will mean, L1 and L2 can possibly be packed. Okay, A1, A2 can possibly be packed. A2, A3 can possibly be packed. A1, A3 can possibly be packed. Okay, and then your dependence edge will say, okay, for A1 to be completed, you actually need L1. For A2 to be completed, you actually need L2, and so on. And then there's something called a focus edge, which means where do you start your search from in a way. So these are the details of your MDP state, which are actually kept as part of this paper. Now, just to go back a bit, The imitation learning that we do here is the following. The actual packing problem, which is called the SLP problem, is solved. It was actually done in another paper 2 years back called Go SLP. It is solved exactly using ILP solvers. Now, this was done earlier, but once again, with ILP solvers, the issues may be if you have very big, set of instructions, the solver may take a long time. So mainly what we try to do is we try to solve small problems using this ILP solvers exactly. And then we try to imitate what the ILP solver would have done when we try to go from one MDP state to another. So basically, you try to model your policy network using a graph neural net. And this graph neural net does nothing else but learn from your oracle, right, which is the ILP solver. And it knows that, okay, if I was in this state, what would have the ILP solver done? The ILP solver would have probably, merged A1 and A2. So I went and did that. And that is determined by your, graph. And so this is the imitation learning part of it. So the way we define the problem is we have our MDP states. We want to go to a new MDP state, and then we have our policy based on a graph neural network, which tries to emulate our SLP solver, our ILP solver. Okay. So that's in a nutshell how the reinforcement learning happens in this particular case. As you may know that we cannot take invalid actions in this case. We cannot have invalid actions like we showed you earlier, that we cannot combine non-isomorphic and things like that because the ILP solver would not have done it. And anyway, those are not valid anyway because you have to choose valid action. So with RL, a good thing is your correctness is guaranteed. You really are not going to generate incorrect code at any point of time. So yeah, that kind of covers the four topics that I wanted to cover today. Maybe I covered it at a very superficial level because we really don't have time to cover them in great details. But these are interesting papers. Please go and read them. It will give you an idea of what people are trying to do in the compiler space for deep learning. And some other work we did not cover, and pretty recently, static neural compiler optimization via deep reinforcement learning, is tries to solve what we were talking about initially. What is the phase ordering problem? Like which pass should I do first, which pass should I do second, which pass should I do third, and is there a good order where it improves performance by doing pass in a pipeline in a certain manner? Because today in LLVM or GCC or any other compiler, the pass pipeline is static, right? You cannot really change it. The other one is a neurovectorizer. It actually is in a work from one of my Intel colleagues, end-to-end vectorization with deep reinforcement learning. So here, it's kind of similar to Charit and someone's work on SLP, but here it tries to predict the best, what are called as vectorization factors for loop vectorization. Like, should I pack 2? Should I pack 4? Should I pack 3? Should I pack more, especially for loop vectorization? And once again, this paper I think is not published yet. One of the very recent ones using reinforcement learning called MLGo, which is a machine learning guided compiler optimization framework. And then Chris has finished his PhD at University of Edinburgh and joined Facebook AI, where he's trying to create a toolkit called Compiler Gym, similar to AI Gym, for exposing all this kind of RL-based techniques and other techniques which people can use as kind of services, right? Okay. And then to wrap it all up, we are kind of coming close to our time. We are just actually at the cusp. It's very early phase. Compiler optimizations and things have been there for many years, 30 years, 40 years. So it's it's not going to be replaced by deep learning techniques so easily because there are a lot of problems to be solved. correctness issues, optimization issues, other issues. And the biggest challenge, I think, is to ensure correctness of the transformed code. And so, as you can see, that's why some of the proposed work has RL techniques. Some of the proposed work has a mix of NLP with some correction algorithms, and no consensus yet on standardized program representations. You saw from Ramakrishna's team that they have done IR to Vic. Similar representation have been done by other people. Some people have just do end-to-end training without actually doing an embedding first and things like that. And also, how do you represent the control and data flow that is there in your program? So some people have tried to use graph neural nets. Some people are, they just don't bother about all this control flow, but look at it just as a sequence of, tokens or instructions. So in my, personal opinion, before we go to that, so some authors very recently, once again, Chris and his guide Hugh Leather, sorry, has suggested something like optimization of service, due to which they are building this, I think, compiler gym kind of stuff. And they think in the future, almost all, if not all, optimizations will be kind of an RL model, based on RL model. But my personal opinion is RL is very costly and probably cannot be introduced for all optimization processes. So I think we'll see a mix, because if you use RL, your really cost of compiling will really blow up, and not all people will be able to afford that. So I think optimization in the future will be a mix of NLP and RL models, very likely. But then the open question will still remain that, can we generate semantically correct transform code always using a DL model? And will there be a mix of DL with some correction algorithms if you're not able to get correct code? And then can these models be really portable across various compilers? So I started with this picture. So let me end with this picture. So my guess, will this be the future, that instead of a traditional analysis pass and a transformation pass, we'll have a learned analysis model and a learned transformational model, and all the passes will be of a similar nature. So that's probably what will slowly happen, maybe several years. And I think sooner than later, we'll see a lot of usage of DL-based and ML-based models being replacing the traditional compiler. At this point, I can take a few questions. Thank you for listening in.